Hey everyone. You ever use an app and it just feels snappy, like insanely fast? Chances are you're looking at the magic of something called an LRU cache. It's this super clever trick that makes systems fast, and it's a total classic when it comes to coding interviews. So let's pull back the curtain and see exactly how it works.
So let's start with a basic problem. Picture your computer's memory like a small, maybe a tiny toolbox. You can only fit so many things in there, right? So when you need to add a new tool, you got to make a tough choice. Something has to go. And what are you going to toss? Probably that old dusty thing you haven't used in forever. Well, that's the exact same problem computers deal with constantly. How to forget things intelligently to make space for what's needed right now.
And that brings us to the LRU cache. LRU stands for Least Recently Used, and it's basically a little data storage area with two very simple but very important rules. Rule number one, it has a fixed size. You can't just keep stuffing things in there. And rule number two, when it gets full, the item that has been sitting there the longest, the one that's been gathering the most digital dust, it gets evicted. It gets kicked out to make room. Sounds simple enough, doesn't it?
Okay, but here's the catch, and it's a big one. It's not good enough for this cache to just work. Oh no, it has to be fast. Like ridiculously, mind-blowingly fast. We're talking about something engineers call constant time, or you'll see it written as O of 1. This basically means instant, and we need this instant speed for not one, not two, but three different things. This is what we call the triple O of 1 challenge.
So, what are these three things we need to do instantly? First up, instant lookup. That means we need to find any item by its name or key immediately. No searching, just bam, there it is. Second, instant reordering. Anytime we use an item, we have to immediately mark it as the newest, most recently used thing. And third, instant eviction. When we're full and need to make space, the oldest item has to be removed in a flash. Poof, gone. And the crazy part? All three of these have to happen in pretty much the exact same tiny fraction of a second.
All right, so here is the million-dollar question. What single data structure out there can possibly do all three of those things instantly? Think about it for a sec. Could a regular list do it? Nah, finding things would be way too slow. What about an array? Not really flexible enough for all that reordering. This is a genuinely tricky problem. It's a real head-scratcher.
And the answer is, well, it's a trick question. There isn't one. There is no single magical data structure that can do all of this on its own. The solution is actually a team-up. It's a combination, a golden combo of two different structures working together, each one covering for the other's weaknesses. And this is where things get really elegant.
So let's meet player one in our dynamic duo, the hash map. The best way to think about a hash map is like a superpowered dictionary or an address book. You give it a key, like a person's name, and it gives you the value, their information, instantly. This is our answer for that O of 1 lookup requirement. So challenge number one, solved. Check.
And now for player number two, the doubly linked list. Now this is the key to our other two O of 1 operations. Picture a chain of items, okay? But in this chain, every single item knows what's in front of it and what's behind it. Because of that, we can pluck an item out from the middle, or add a new one to the front, or remove one from the very back, all without having to rearrange the entire chain. It's super efficient. And just like that, we get our instant reordering and instant eviction. Challenges 2 and 3, solved. Double check.
And there you have it. This is the aha moment. You take the insane speed of the hash map and combine it with the incredible flexibility of the doubly linked list. The hash map handles the speed, and the linked list handles the order. You put them together, and you get the perfect, super efficient O of 1 LRU cache.
Okay, so we have our dream team, right? The hash map and the doubly linked list. But how do they actually play together? Let's pop the hood and see this thing in motion. We're going to walk through the two most important operations, what happens when we get something and what happens when we put something new into the cache.
Here's a really great way to visualize this. Just imagine every item in our cache is a card, and they're all linked together in a long chain. That's our doubly linked list, right? With the newest card at the front and the oldest at the back. So what's the hash map for? Well, the hash map is like a magical index that points directly to any card in that chain. So you never have to search through the whole deck. You just know exactly where to go. All right, let's walk through the get operation. Say you need an item from the cache. Step 1, you use the key to look it up in the hash map. That hash map instantly points you to the exact node in our linked list. Now here's the clever part. We give you the value you wanted, but at the same time, we unlink that node from wherever it was in the chain, and we move it right to the very front. Why? Because you just used it. It's now the most recently used item. And because it's a doubly linked list, that whole move happens in, you guessed it, O of 1 time.
Okay, now for the put operation. What happens when a new item comes along and our cache is already full? Well, first, we create a new node for this new item and we stick it right at the front of our list, because it's the newest thing. We also add it to our hash map. But wait, now we're over capacity, so what do? We look at the poor node at the very end of the list, that's our least recently used item, and we simply remove it. And, crucially, we also delete its key from the hash map so we can't find it anymore. Both structures are updated, everything is back in balance, and it was all done in one smooth O of 1 move.
So yeah, that's how it all works. But what about the why? What makes this design so brilliant and so common? Let's talk a little bit about the payoff and why this exact pattern is a cornerstone of so many high-performance systems you use every single day.
It really just boils down to this beautifully simple idea, using the perfect tool for each part of the job. You've got the hash map, which is our speed daemon for instant lookups, and then you've got the doubly linked list, our master organizer that keeps track of the order. Each one is great at one thing, and when you put them together, they create a solution that's basically perfect.
Now, it's worth pointing out that LRU isn't the only game in town. There are other strategies out there. You've got LFU, which is least frequently used. It cares more about how popular an item is than how new it is. Then there's simple old FIFO, first in, first out, which is easy, but kind of dumb since it might kick out something really important. But for a huge number of use cases, LRU really is that Goldilocks solution. It just works. It's just right.
Okay, so if you're ever in a coding interview and this question pops up, and trust me, it does, here's your playbook. You lead with the answer immediately. I'd use a hash map and a doubly linked list. Then you explain the logic. The hash map gives you O of 1 access, and the linked list gives you O of 1 reordering and eviction. And for bonus points, make sure you mention that even a get operation is technically a write because it modifies the list by moving the node to the front. You hit those key points, you're going to look like a total pro.
And all this leaves us with one last big question to think about. An LRU cache makes a big assumption. It bets that the thing you used most recently is also the most relevant. But is that always true? What if something is used very frequently, but just not in the last few seconds? The answer, of course, is it depends. It depends entirely on what you're building. And figuring out that trade-off, well, that's what being a great engineer is all about. Thanks for tuning in.